CubeSat for the FUNSAT competition that we designed for NASA. Basically, just to give you a little background, the first half of the presentation is going to cover up to the competition, and then afterwards it's going to go on modifications that we made following the competition. To give you a little bit of a background, the CubeSat is, as you see there, a miniature satellite. The one we designed is the far right one, FIU. Basically, the focus is a 10 centimeter by 10 centimeter base with a 30 centimeter height. The reason we chose this sizing is because of the components that we needed to put inside here. To go with smaller components, it was significantly more expensive, so we had to kind of play around with the weights as well when we were considering choosing the components for each system. This is our timeline for during the whole course from Senior 1 to Senior 2. In May, you see a little highlighted box with the final design. That was when we participated in the competition, and a breakdown for basically each subsystem among each individual member. We wanted to focus for the global aspects on, it didn't just have to be anything for temperature monitoring or image capturing for just the US or specifically for FIU. As long as we're able to get a signal from the GPS tracking system, we can basically send this anywhere we want. Another reason was we wanted it to be modular, so with any type of payload that we want to use, you can swap out the parts easily, reuse them in any way that you see fit. Like I said before, we wanted to make it recyclable. Anything that we wanted to choose, especially for the chassis, we made out of aluminum. Anything that you can add on, simple brackets, easy installation. As for the components, same thing, that you can use them for different types of systems. The main feature that we used to interface everything was the BeagleBone Black. So you can easily program this using Linux to specify any type of payload or any type of program that you need with any electrical system. Now, for the two key factors that we were judged on for the competition, the design portion, which is how unique your payload is, what makes you stand out from the other CubeSats in the competition, how everything is laid out and interfaced, and then the second part is the manufacturing and the physical prototype, what you see. Now, we got some good feedback from the competition. Unfortunately, we weren't chosen to actually launch our CubeSat into space. The main reason that they specified was, since we were doing a new system that's never really been developed for this size, the sailing system, they didn't feel that our group had the backing or the knowledge to support such a project. So the top three teams that they chose already had affiliations with NASA. They already had experience in the competition. They basically saw us as the baby in the project. Now, this is the initial structure. We had all our electronics set up to this portion, the sail housing here, and the deployment system at the bottom. We wanted to make it as lightweight as possible, slotting as much as we could, reducing a lot of the weights, and we chose the aluminum 6061 for the strength of the whole chassis. Now, for the new objective, after we went to the competition, we're still doing temperature monitoring and image capturing, but the emphasis is going to be on the sailing system that you see the deployment of it as well. We're no longer using the rocket launch just because to send it out into space would just be way too expensive, so we found a company that actually does a balloon launch that I'll explain in a little bit. As far as for the constraint set, we didn't have to follow the sizing restrictions set by the competition, so we exceeded that by a couple inches vertically. Now, the company is based out of California. It's called Global Western. They do all sorts of unique missions for weather balloons. When we contacted them, they said that they could launch our device for up to 55,000 feet, possibly higher. But it just, for the time constraint and the cost that we were going through, it would just be our basically only option for testing this. And now we're going to talk about the electronics here.
So some of the three major things that we were looking at for the CubeSat itself was power management, communications, and altitude control. The power management, we have to have enough power to actually power everything that we have on there. Specifically, we need 12 volts just for the stepper motor itself. Communications, we have to be able to have a way to actually communicate with all the different subsystems that are in there, mainly the 9 degrees of freedom, the temperature sensors, from the CubeSat to a ground station if we were to when we would have one. And then for the altitude control, we need to know how well this thing is orienting. Whether or not it's in the right path, whether or not it's slanted, whether or not it's pointed in the right direction, or whether or not it's upside down. So for the current payload, just for testing reasons, we were using a Logitech C525 HD camera. It provides 8 megapixels camera, so we're already above that threshold where more of a higher resolution probably isn't going to be noticed that much. we were mainly trying out a program called GutView, which is readily available for all BeagleBone Linux, to be able to capture images and video, and be able to save it and then do whatever we wish with it. Now, in the upper left-hand corner, you'll see that we have a pretty big window to see the images that we're capturing. But one of the issues that when we were testing it was that we were having like about a 2 to 3 second lag in regards to the information that we were capturing. So if, let's say I would move my finger, it would take about 3 seconds just to see it move. So you can imagine if you were trying to monitor something, okay, we're 3 seconds behind something that already happened. So you can imagine how that would be a problem. What we did was just, luckily, the program itself is able to reduce the amount of the size so we can actually be able to see the images better, so we reduce the resolution. We do reduce the amount of the size that we can see, but we reduce significantly the amount of lag that's between each frame. And on the bottom picture, you'll see that we actually are able to save it to the BeagleBone itself. One of the issues that we noticed that whenever we lost power or we turned off the BeagleBone, we would lose those images. So what was happening was that we were able to actually use the same program to actually change the location of the save file. So for instance, we now have them saved onto an SD card. Now for the temperature monitoring, we were using a TMP36 sensor. It is an analog sensor, so it just what it's going to be doing is taking the voltage readings from that sensor and then be able to interpret the temperature that is based on that. This is just some sample code that you'll see. At the moment, we're setting up a specific pin on the BeagleBone itself, mainly pin 9_40, to be able to receive the voltage data, and then later convert that millivoltage into different types of temperature, mainly the degrees Celsius, Kelvin, and Fahrenheit. There was also another thing that we included on there was basically a function to get out of the program. At first it was just constantly giving you data, but you had no way of knowing what to do exactly to get out. On the right hand side, you'll see that the temperature, we're seeing a constant temperature of 70 degrees Fahrenheit, and then the corresponding Celsius and Kelvin. Then later when we tried to change the temperature around that area, the temperature would change, and then we'd have anywhere from 70 to 75, which was the last temperature change that we tested it with. Now, the 9 degrees of freedom. This device, like I said, it has a 3-axis accelerometer, gyroscope, and magnetometer. With this, we would have been able to actually to determine the positioning, the direction, and also the g-forces that it's experiencing. Now, one of the issues that we did have was that we had no clue about was that in order to actually work with the pins in regards to digital signals, you had to write an entirely new program for that specific pin in order to actually get that information, which was outside of our own programming capabilities. So now I'll hand it over to Luis to talk about the deployment system.
Since we didn't get picked in NASA, we tried to redesign our whole cell system if we want to launch it with the weather balloons. The original design was designed to work with solar winds. Then we changed the new design to be able to work with wind speed. This is the original design. That's it. This new design, we have a motor which is transmit the force to the gears, and is able to move the whole cell system. This is a retractable system. So when we don't want to move the whole satellite, we just close it. Also, we extend in the original design. We extend the side panels 4.5 inches to get a space for the new cell system. The total weight of the cell system is the heaviest part of the whole satellite. It's about 7 pounds. The whole weight. The total weight with the cell system and the other components is about 4.9, which is a little bit higher than the specification for the competition, but it's a really fair number based on the changes we did to create this new cell system. Like I said, the weight is very important when we do the launching. We did some weight reduction on the rail. We came up, after we did all the slot, we came up with 0.29 pounds per rail, and at the end the total weight reduction was a little bit over 1 pound, which is a really significant number if we take into account that the whole weight of the project, the satellite, is 11 pounds. This is the welding. We did 2 weldings in the whole structure. This is all aluminum welding. One was to create the structure. In this one we realized that the plate, this is 1 millimeter plate thickness, and the thickness of the rail is about 0.5 inches. And since they have 2 different thicknesses, the welding temperature for them is different. You have to go higher on the rails than in the actual plate. We did it for the first 2 plates, but when it came to the third one, we have a little bit of problem. Some of the plates were bending a little bit, but then we got some help, and we finished the welding. And in the cell system part, this one we have to change the welding because the bearings are plastic. So we did the connection between the boom and the shaft with electricity. First thing we need to consider to pick this motor, this specific motor, is the wind speed we're gonna face during the mission. This chart gives you the wind speed at different altitude. The highest wind we're gonna face is about 90 meters per second. So we base all our calculation on that specific number. At the end, with all the information, we calculate the area of the cell we need in order to move the whole satellite. We need since this is a retractable system, we have to the torque needed was about 30. Since the retractable system, this motor has 35 inches-pounds, so it's able to close the whole system when the cells are facing the wing.
Okay, I'm going to talk about the gear design. Once having calculated the motor, the stepper motor, we proceed to do the gear design. We follow 2 standards, the ANSI and ARMA standards, to prevent any type of interference and also optimize the performance of the gear set. We take it into account 5 considerations before proceeding, doing the gear design. One was the minimum number of teeth for a given pressure angle. Second was, in order for this system to work, we need to have the same number of threads, also the pitch, the diameter pitch, and the pressure angle. The third was the axial pitch of the worm and the circular pitch of the worm gear needs to be the same in order for this to work. The last 2 was to consider higher pressure angles lead to higher tooth strength. And the next one is the lower pressure angles are better suited for higher speed and also quiet operations. Here I'm going to talk about the worm gear design first, then I'm going to go ahead and talk about the worm analysis, and then of the whole gear itself. We selected a 14.5 pressure angle worm gear because of lower bending tooth strength and its lower bearing stresses. Once we have determined the 14.5 pressure angle, we then go ahead and determine the number of teeth. We selected a 14 teeth with the 12 pitch diameter pitch because of the gear ratio between the worm and the worm gear was 40. And we use those following the ARMA standards. Here's some of the calculations we did to find the worm. Once we have calculated the worm gear, we selected to be a single thread, 12 pitch, 14.5 pressure angle. We then calculated the worm pitch diameter using the Agnew equation for good power capacity. Our calculations came out to be 0.87 inches, which it was fairly close to what we selected to be 1 inch. So then we used this equation, as you can see, to find if our pitch diameter was in between the allowable range. We found that the minimum was 0.665 and the max was 1.157. Once having calculated our worm and worm gear, we proceed to do the whole analysis of the gear set. As I mentioned before, the worm axial pitch needs to be the same as the worm gear circular pitch. And here our calculations show that it was 0.26 compared to 0.262. Then we proceed using those equations to find the lead angle. Our lead angle came out to be 4.76. And since we're using a single thread worm, our lead angle equation should be also related to the 90 degrees minus the helix angle. Our helix angle was found to be 85.74, giving a lead angle of 4.26, which is fairly close to our calculations found to be 4.76. Then it was later verified using our textbooks. With a pressure angle of 14.5, it should fall in between 0 and 15. Here is some of the calculations we did to find the forces. It was really important to find those calculations because we needed to find the bearings. Our calculations were found using those equations, and later we determined that it was 80 pounds for our radial load and 124 pounds for our axial load. With those two calculations, we then go ahead and purchase our bearings. The bearings selected were flange bearings, and those are the loads that it supports, so we were okay with those two. And those calculations we're selecting using the momentum over 2 planes. Here we have our video of our prototype when it closes. And this video also shows when it opens.
So the price breakdown that you see here is basically the whole system, not just the sailing system. We also received funding from Dr. Tansel and to include the travel to the competition. So we were roughly looking at about $3,000. We understand that when you send anything into the skies, there's going to be some sort of risk in terms of tracking your system, any type of wildlife maybe, or anything like that that might damage the CubeSat. So we wanted to take into consideration the GPS system was fairly easy to use in terms of tracking our CubeSat, and we wanted to reduce any sharp edges in the system itself just to minimize the harm that we can do in any case to wildlife. We definitely learned a lot from this whole project. We had to work with numerous departments, a lot of cross-platform collaboration basically to try and develop this whole system. It was definitely helpful on the manufacturing side as well. We had no serious experience with welding. For future considerations when redesigning the structure, we might consider stainless steel just because we went through a lot trying to do the aluminum welding. From this project, we were hoping that a lot of the courses here in FIU don't really have a focus on aerospace. They offer a couple electives, but we were hoping to increase the awareness that we have with our project to maybe stimulate a new field of study for this program. And hopefully we're going to continue this project, maybe compete with a club that we're starting. We just got a CubeSat club approved. We're still trying to raise the awareness for it to get funding from the school, but we want to continue this competition as something similar to SAE, but in terms of aerospace. Special thanks to Dr. Tansel. He was able to help us out with the funding, a lot of money and a lot of time for the research that he was able to provide. Dr. Gooving supplied a lot of components in terms for the GPS tracking. Dr. Ziccarelli, he actually helped us a significant portion with the manufacturing as well, with the gear. And Pradeep, our mentor, he was kind of overseeing the whole project, making sure that all the teams were working together, mechanical, electrical, computer. Rocio was helping us a lot with the collaboration with the vendors, trying to order all the components. Arvin and Gabriel were our main contributors to the programming as well. Anytime we had any debugging issues with Linux, they would always step in, and various people throughout the departments actually helped us to put this together. We just had some pictures from the CubeSat competition with a couple other groups, and that pretty much wraps up our presentation.
May I start?
Yes, go ahead.
When you're welding the aluminum, how are you welding? Were you using acetylene gas or?
Yeah, we basically just go to Home Depot, one of those torch kits that they sell. The only problem was that the thickness with the rods was so much more significant than the walls that when we would try to do 2 walls, we would be successful with it. But on the 3rd wall, it would sometimes heat the whole panel that it would separate the other welding. So yeah, so we were taking 1 step forward, 2 steps back at that point. That's why we had some success.
Because I know we have a TIG weld in there, really TIG weld is really the best way for welding aluminum. The one problem with aluminum is like a regular steel, it gets cherry red and then the molten.
Yeah, it started deforming also.
Right.
As we were doing
With
it.
aluminum, you don't see it turn red, it just melts.
Yeah, we definitely ran into
So,
that.
but using a TIG welder, because they use an argon gas, you eliminate any contamination of the weld by pushing the oxygen out of the way. And with the TIG weld, you can really control that polymer very well and use it to create a weld.
Right.
And one thing you might want to do, instead of doing one long bead, because that's going to make it deform on you,
Just
jump around.
Yeah.
So just suggestions, but I was kind of curious how you were welding. Thank you.
Yeah, I was going to say, in the report, you basically said that you were going to perform vibration testing, thermal testing, and deployment testing, but I didn't see the testing in the report. Did that work ever get done?
Unfortunately, when we switched from the competition, we couldn't. The only simulations we were able to do were through SolidWorks. No physical testing that we could do with our system. For the vibrations, the company that we contacted, they didn't have any chambers available to hook up our jig to. So it was basically a matter of time and availability to conduct those testing.
Okay. You also made a statement here that you needed to changes to the payload, the structural design, the sail, deployment design, and the overall function of the CubeSat. Were these changes made?
This is, you can see as I said before, the original cell system was designed to work with solar wind. Since if we do the launcher with the rocket, you get to space, and then we get to move the satellite with solar winds. But since we didn't get picked in NASA, we tried to redesign the whole cell system to be able to work with solar winds. And this is with the weather balloons. Since we didn't have to keep following the specification for the competition, we made this change to be able to work with solar winds and be able to do the launching with the weather balloon.
Okay, and then my last question is, you communicated that the max winds would be about 90 meters a second. Will those sails survive at 90 meters a second with the seams and all?
I'm sorry, it's not 90 meters, it's 90 feet.
90 feet a second?
90 feet a second, yeah.
27.
Yes, the cell are made of polyester, which is based on my investigation, is what they really use. That's the material that they use a lot
Seams.
for.
I'm worried about your seams. I'm not worried about the polyester.
You mean the boom?
No, the bond that you've got around the wire frame.
How it's holding the sail onto the wire frame.
We get glue, but this glue is able to work with water and the temperature, so the cells doesn't fall apart.
So he says, like, is it gonna hold up under that maximum expected wind?
You're basically pulling out like this. And then-
Oh, yes, yes,
Am I
yes.
gonna-
That's true.
Yeah. Yes.
Okay, thank you.
And so that's aluminum, that reinforcement, that line,
That's stainless steel.
stainless steel. So even that bending moment, I mean, that's,
Right.
what, 2 feet or something, right? 3 feet bending moment on the end of that really, really thin stainless steel rod, right? And so wind forces of 27 feet per second, you said, right? 27? 90 feet per second, okay, 90 feet per second. Are you're sure that those, I mean, that's a pretty important part, right? You say yes, but
Yes, I know basically, I did the calculation for the material.
But for the material, right?
Yeah, I know.
Just the material.
We did it also for the specifically just the rod in the SolidWorks, and the numbers we got, we didn't have any significant bending on those booms.
So what was the force on the end? Just curious.
The force on the cell.
Yeah, sure.
The
So
wind pressure.
what's the resultant force?
The result of force, the total wind pressure was about 2 or 3 psi, something like that, and the whole structure is able to hold to 15 or 20. It's in something in that range.
I have a real quick solution to answer that question. You got the wind tunnel right there.
Right.
I know we figured out that,
Or
but
just
then we have to get
put
some
a plate on there with
appointments.
some weights, right? Yeah.
It's
you can
because we didn't do the testing here, the wind testing here, because we have a little bit problem with the tank, and then we talk to the people in the lab, and then we have to get an appointment for it.
So you can just see what it does, real
Yeah.
wind hidden, and then you really know if those rocks bend or not, you know.
That's something that we're actually looking forward to continue. If we get some more, we already started this organization, so hopefully, we get more people to join in, and that should be something that I think it should be, and it really should be done in the future.
But our final goal is do the lecture.
Can I go one more quick one? Sorry.
Yes, yes.
Can you go to the slide where you had just the comments from NASA? Whoa. Zoomed in.
Everything grew.
I feel like the plus button. There we go. So just from the comments that you guys heard there, I mean, the first part, they said the main drawback was lack of discussion of pointing requirements for the science. Right? So, did you try to fill in some of the issues that they had with your science as you went along? That was in May, right?
Right, but the
Yeah.
feedback for this was for the whole system, so we didn't
Okay.
bring all the electrical components and discuss in its entirety how everything interfaces, so that's what they were referring to.
Okay, all right. Because it seemed to me like they were saying you didn't do enough analysis.
No, that's
to
not
convince
directly,
us.
that's not.
Okay.
No.
Okay.
Actually, they were really impressed with the original design of the solar wind, of the solar system, because we were able to hold 10 meter square area in 10 centimeters square. So
Right. Okay, thanks.
I think main problem is because of the change they had to make in the design,
Yeah.
that cost them a lot of time, and it really prevented the testing. So that's the excuse, if you will, but otherwise it's because they designed two systems actually for months. So, plus, they're taking a bunch of the courses.
It came to a point that we were, at the summer, we all were getting internships. It's not an excuse, but, we also had to change the design. And since we had to change the design from point A to point B, and it was no more to be done, we decided to use the wing as an option and put our engineering skills to to design the gears, and make this work, make it happen, so we can show something to you guys at the end.
How do you respond to point 2 and point 3 today?
Yeah, those are the questions that we asked.
I think they were talking about the how much voltage consumption and how everything was interfacing once we had everything working operationally, not to blow any.
There's no voltage in aerodynamics.
No, I'm talking about for the other components.
Number 3.
Two. Yeah.
I would like to
No,
give
no.
a say for that. Point number 2.
Number 3.
Right.
Point number 2, that was for actually for the final proposal, which we told them that we'll be doing this. However, simulation results were only the thing which was missing there in the results. When they went to there, they had a discussion with the professor. I forgot the name of the person. So that thing, and the third one is the quad component is like basically bringing the system from the off the shelf of the market and then putting it like in the existing satellite. But however, that was proposed for the final thing, which we didn't meet there.
Any other comments, Stephanie? Thank you very much.